You can have a look here. Problems are very simple. The first problem. The armature of a 6-pole 600 revolution per minute generator has 90 slots. These slots are 90. Okay. The armature of a 6-pole. It's not a two-pole machine. It's a 6-pole. 3 north pole and 3 south pole. Okay. 600 revolution per minute generator has 90 slot. Each coil set has 4 turns. So if I put 4 turns, it's going to be 1 coil. It means I need to wound like this. In the slot, this is my slot, I'm right. Here I have to put 1, 2, 3, and 4. Okay. This is the meaning of 4 turns. So each coil has 4 turns and flux per pole. Each pole, you know the meaning? Each pole will produce 0.04 Weber. Calculate the value of induced voltage. You have my slides. You have the formulas. You can easily find. How to do that? Please use your calculator. So what is the formula to calculate the output voltage, induced voltage? Listen here. Z N phi divided by 60. So I need to know what is Z, what is N, what is phi. Z is the number of conductor. N is the speed. Speed is already given in revolution per minute. And I need to calculate what is the flux. Flux is also given in the problem. 0.04 Weber, right? Is already given. Calculate what is Z. How to calculate Z? Z is equal to the formula is number of coil into number of turns per coil multiplied by conductor per turn. So how to calculate the number of conductor Z? Number of coil multiplied by turns per coil multiplied by conductor per turns. So in the problem, I have 90 coils, 4 turns per coil, 2 conductor per turns. You all multiply, you get 720. What is the speed of the machine? 600 revolution per minute. Now I know the value of Z. I know the value of N. Phi is already given in the problem, 0.04. Find the answer. You should get 288 volt. Try. Right? Please use smart calculator, advanced calculator, not with Wi-Fi. There are many calculators which can help you to solve a big arithmetic equation in simple way, but please use the prescribed calculator from the university. For me, it's not a problem if you use advanced calculators, but not with Wi-Fi. No. Wi-Fi, Bluetooth, no. Maybe my answer is wrong. Try to verify. Please don't believe 100%. You have to calculate. Yes, 6 volts. Sorry. This is the problem. The armature. Yeah. Yes, 90 slots. Yeah. And here. 6 volts. Yes. Pole is not required for your calculation. What is the formula? Number of coils multiplied by turn per coil multiplied by conductor per turn. This is, you are going to calculate how many conductor. So your armature, I'm right. Listen here. We are going to calculate this total coil into number of conductors. Is a set of coil. I'm going to know how many conductors is inside. This set. Z is the number of conductor. How to calculate? Number of coil. How many coil you used? Multiplied by turn per coil. How many turns? For example, if given 4 turns, then here I'm going to keep in one slot 4 turns. Yes. Then conductor per turn. How many conductor you are using per turn is already given in the problem 2. So you multiply all, you get 720. Please verify. Then you have to calculate what is induced voltage. So each conductor, how much induced voltage they will produce. It's going to be 288 volt. It's okay.
We always two conductors.
Sorry, it's Z is equal to 720. Z equal to 720.
I mean, two conductors transfer.
Yes, per turn, yes.
It's always two.
This problem,
Yes.
for this problem, we have 2 conductor per turn.
And we get the information from there.
195. Here I mentioned 2 conductor per turn. Nobody asked me a question. How I find it? That's why I told you, be cautious. Otherwise, you will not learn. So we have 2 types of winding, lap winding and wave winding. We will discuss it, okay? Because I don't want to make it more complex. Very simplest way. This design is based on lap winding. In any lap winding, it's simply have to take 2 conductors. So please write it in the bracket here, lap winding. Just write it here, lap winding. Take a note. Otherwise, that's why I didn't give you in the slides. You have to learn. I given you all the slides. Otherwise, it's directly the answer. Please write it in the bracket, lap winding. If the design is done for any DC machine with lap winding, you can directly take 2 conductor per turns. It's okay. We will see later. Don't worry. Can I go to the next problem? This problem is available in your textbook. Please go to page number 76, solved problem. Okay. I'm going to the next problem. The generator shown in the figure below generates 240 volts. So generated output is given 240 volt. The same figure I showed you in the lecture slide. Have a look. I given you an example for 72 coils. I showed you how the neutral axis will created between the poles for a big machines, not 2 pole, more than 2 pole. The same diagram. The generator in the figure below generates 240 volt between adjacent brushes. Adjacent brushes. These are the adjacent brushes. You can have a look. 1 set, 2 set, 3 set, like set of brushes are here. So this will give you positive and negative. This will give you positive and negative. Like that, we have a set of brushes. The generator in the figure below generates 240 volt between adjacent brushes and deliver a current of 2400 ampere to the load. Very high power. Calculate. Number 1, current delivered per brush set, the current flowing in each coil, the average induced per coil, voltage induced per coil. So these are the 3 questions. If you look at my slides, all the formulas are readily available. Let us do the calculation. First step. So they are asking you to calculate what is the current per brush set in the first question. So how to calculate? You already know what is the total current of the brush. 2400 ampere is coming out in the plus terminal. Of course, it goes to the minus terminal, the same current. You know what is the meaning of the current between plus and minus is going to be 2400 ampere. And in the problem, they given 12 brushes. So the 12 brush, what is the meaning? 6 can be positive, 6 can be negative, not uneven balance, right? 6 set can be positive, 6 set can be negative. Please note, in this case, we have only 2 brushes. Look at here. One is plus, one is minus. When you have 6 sets, when you have 12 brushes, what is the meaning? 6 can be positive, 6 can be negative. That's why we have taken 6 positive and 6 negative. Then how to calculate the current? Divided by number of brushes. That's it. The total current divided by number of sets. How many sets you have? 6 sets. two brush for positive or negative, one set. So then we'll have 6 sets divided by 6. So the total current is added up among the 6 brushes. Clearly, for example, this is a 10 ampere machine. What you will get the current here? 10 ampere. For example, if I place another 2 brushes here, what is the current? This is 5 ampere, this is 5 ampere, 10 ampere. Clear? So total current is 2400 divided by 6 sets of brushes, not 12. 12 is the total number, but you have to split which is positive, which is negative, always even number. We can have only positive where we go for negative. So one set is plus and minus. Is okay? Second question, they are asking you the current flowing in each coil. What is the current in each coil? Each coil, what is the current? For this, we have to calculate. We already know what is the total current given in the problem is we already calculated the current through each brush set is 400 ampere. So that divided by number 2. So then you get 200 ampere is your current flowing in each coil. What is the current flowing in each coil? We can have only positive coil and negative coil. There are 2 possibilities. So the total current you already know. What is the current from each brush set is going to be 400 ampere. Divided by 2, you get current in each coil. Where this principle comes, listen here. I already showed you one picture. So coil number 1. Listen here, coil number 2. That I place something like this. 40 ampere, 40 ampere. The output is 80 ampere. I'm right. The same detail here. So I have set of current coming from my brushes. Then I have only 2 coils. These 2 coils. How they share? 40-40. Here it is 400. So here 200 ampere. Here 200 ampere. I will get 400. It's clear. So it's going to be 200 ampere. So totally 200 ampere I will get. Any doubt? How the current is shared between? So the total current is going to be 400. The total current is 400 ampere. How each coil separates? 200, 200 ampere. It's clear? Then I get total 400. So the brush is between coil 1 and 2 is an example. Can I go to the next one? The average voltage induced per coil. What is the average voltage induced per coil? How to calculate? There are 6 sets of coils. 12 coils. We have 6 sets for plus and minus. So I know the voltage, which is going to be 240 given in the problem. You can have a look. Generated voltage across the coil is 240. 240 divided by 6. Each set of coil will give you 40. Clear to you? The average voltage per coil is 40. We have 6 sets. All the 6 will add up. You get 240 at the output. So you are getting an output 240 because all the 6 will add up and you are getting out. Clear to you? Please have a look on this problem. This will amplify your theoretical background very easily. What is going inside the machine? Any doubts? If you all solve the problem, I will go to the next part. So don't forget, 2 conductor per turn is standard. Or most of the machine in the world are lap winding. Very few application we use wave winding. We will see in the next slide what is lap and wave. Any doubt? Anyone having any doubts, please let me know. So in the examination, I will not give you the answer. So you have to choose. This is 2 conductor per turn. I will again repeat this problem in the theory. Another part it is required. Can I go to the next problem? If you all okay, can I go to the next problem? Okay. Problem number 3. Can I go? A 4-pole 250 kilowatt 750 volt DC generator has a lap winding on the armature. Calculate the full load current of the generator. Full load current of the generator. What is the full load current? The current carried by the armature coil. What is the current carried by? What is the armature? Don't forget in your life. Rotating part is called armature. What is the current this will carry? See? Let us solve the problem. So I have 250 kilowatt. I'm right? 250 kilowatt. 103 is your you have the power. Power is 250 and your voltage is 750 into I. Calculate what is I. How to calculate the current? Power equal to V into I. Power is 250 kilowatt. Voltage is 750. So I can easily calculate what is my current. How much?
330.
300? 3. So there is a small error here. Please change it. So 333 ampere. Answer is correct, am I right? So this is just power equal to V into I. 250 kilowatt equal to 750 ampere into I. Please change in my side. I have to correct because it's a typographic error. I is equal to 250 divided by 750. You get 333. Answer is correct. Okay. How to do that? Simple formula. Power equal to voltage into current. Here it is 250 kilowatt. The voltage is given 750 and I. From here I can able to calculate what is I. 250 kilowatt. Don't forget the unit and 750 ampere. Then you get 333. Sorry, volt. Then you get ampere. So please put the unit. That's very important.
We get that 103 from.
That's a typographic error. Please calculate. You're getting the answer for this one or that. Please verify.
Yeah.
That is a type in the typing. You know, I'm typing. I done some mistakes. So this happened. Okay. It should not be there. That should be kilowatt.
All right.
You got the answer? Do this procedure. Are you getting?
Yeah, all right.
You got it? What is the next one? Next question. The current carried by the armature coil. What is the current carried by the armature coil? They are asking you. For that, what we have to do? There are 4 poles. Obviously, if there is a 4 pole, 4 brushes. So 2 brushes for positive, 2 brushes for negative. That's why we mentioned 2 positive brushes, 2 negative brushes. I already calculated the current. The total current is going to be 333 divided by number of brush sets, not the brush number. So there are 4 brushes, 2 sets. So 333 divided by 2, you get 166.5. So this is dot. When I am typing with Word, I done some errors. So this is not copied from your textbook. I type. So 166.5. Calculate. Do you understand how we are getting 160? Because there are 4 brushes. Listen here. 4 brushes. 2 for plus and 2 for minus. Taking the minus out. Then we have 333 divided by number of brushes. 2. You get 166.5 ampere. Is okay? How I calculated current per coil? Anyone? Current per coil. Current per coil is 83.25. How I calculated? Anyone?
By the number of poles.
Number of poles is correct. If it is going to be a lab winding, no problem. If I give you a wave winding, that is another problem. We'll learn next slides. Look at here. What is the number of brushes? Here I calculated set of brushes. Okay. But the brushes are connected. One brush will be connected to set of coils. Another brush will be connected to another set of coils. Right? So each brushes are connected to set of coils. Then we assume this is positive, this is negative. Right? But I want to calculate what's the current through each coils. Nothing but divided by number of brushes. So it's not by 2, it's by 4. You get 83.25. So how to calculate the current through your coil is nothing but the current what you calculated 333 total current, armature current, divided by number of brushes, not number of brush sets. Number of brushes is 4. Divided by 4, you get what is the current through the conductor. Why I am telling that? Your number of sets of coil. I'm right. These all are connected to one set of brush. I want to find what is the current through the conductor. One set. You understand? Then I should divide it by number of brushes, not number of brush pass. I should not combine the brush plus and minus. I should find for individual coils. So divided by number of brushes, that is 333 divided by 4. Okay. Last problem, we will look after the theory. Let me go to the next slide. All finished. Please write it in your answer how to calculate the current through the conductor, the total armature current divided by number of brushes, not number of brush sets. Look at my diagrams. A set of conductors or a set of coil will be connected to one brush. There are 4 brushes. We will put 4 different brushes and we pair 2 as positive, 2 as negative. But I'm concentrating on number of conductor, how much current is going to take is one set. So divide by 4. If you have any doubts, you can also email me. You can come to my office about if any parts of the electrical machine is confusing you. Next, we are going to finish because only 4 slides. Comfortable. So these are going to be the different types of your electrical machines which are used in real time across Europe and other countries. This is an example. You can have a look how big. This is a stator. Stator is a fixed part with an electromagnet. We call it as a field winding for DC machine. which is having 9 megawatt, 250 RPM, 1650 volt speed. This is used in mills, large scale mills is an example. This is another motor you can have a look, which has a rotating part armature, 5 megawatt, 60 per 120. Please note, as the machine increases the size, speed comes down. When the machine is very small, this machine can run at 3000 RPM. This machine can run at 3000 RPM. When the machine of this size, building size, the speed comes down. So speed and the size are inversely proportional. If a very big size machine, speeds come down. Small machine, very high speed. It's clear? So speed and is a practical. When the weight is very high, I'm right. As the capacity increases, the weight is very high. So the size is inversely proportional to speed. We call it a small n in your textbook. Okay, they are inversely proportional. And this is an example where you have 8 megawatt. I'm just giving an example. Capacity is very high. If you go near to this machine, you will feel the heat. 8 megawatt. See the speed, 50 bar 100 RPM, very small speed. DC reversing mill motor used in mills, operating at 899 volt. And this is an example. These machines are used in Siemens, Munich, Germany. And this is used in Canada. A large synchronous motor in mining industry. You can have a look how the real-time machines, not like this, small pony motors. And this is an example of vertical synchronous generator, power generating unit. If you go to any hydro power plant, you will see the machine something like this. The water's flow rate will be converted into electricity like this. And this is an example of a very large motors which is used in metal industries. You can have a look. What is the size of the machine in real cases? What we are talking in the lab theory lecture here are very simple, but in real time is very, very big. Then I am going to classification of DC machines. I already given you in the beginning of my presentation. I explained you DC machines are classified into two types: separately excited, self-excited. I want to give you in a very simple format so that you can easily have an idea what is this classification. What is self-excited? What is separately excited? So I have two indexes, am right? One is my electromagnet. So this is my electromagnet. I put little terms. This is my electromagnet. But here I called as field winding for DC machine. This is my field winding. And this is my rotating winding. I call it as armature in DC. Okay, I have two. One is fixed, one is rotating. This is a concept. How I am going to apply the power, that is the concept. If I use separately a DC for this one, I use a DC power supply for this one, plus and minus. I give a plus and minus here, separate DC source. Here separate DC source. This is called separately excited. I give DC power supply separately to the rotating part. I give DC power supply separately with another source to my electromagnets. Then it is called separately excited. It's clear to you? This is called separately excited. I have two windings. This is my electromagnets. And this is my armature. I use the same power, DC supply, plus and minus. This is called self-excited. This is my field winding. I'm going to put it as FF. This is my armature winding. I'm going to put it as a AA. So this is my rotating armature. This is my electromagnet, which is called field winding. I have only one power supply. This is called self-excited. Look at the connection, how they are connected. Starting point is connected. End point are connected. This is called shunt DC motor or DC generator. But what is the meaning? They are parallel. So I call it as also parallel connected windings. So this is called shunt DC motor. This is called separately excited DC machine. In general, I'm telling you, motor or generator is different, but how it looks the same. Then we have series. What is the meaning of series? I have a DC power supply. I have this field winding, F. Then I connect in series with my armature winding. This is called series DC motor. That's it. Clearly, with two winding, I explained. Two set of inductors. If I put it in parallel, they are called shunt. If I put it in series, they are called series. I use only one DC sources. That's why it is called self-equivalent. Clearly, if I use two windings separately, I power with two different DC sources, then they are called as separately excited. Clearly, separately excited means two coils I generate with two different power sources. Okay? Any doubt? Now let us go inside each characteristics of the machine. First, let us see what is a separately excited. So separately excited, you can have a look. This is my north pole. Listen here. This is my north pole. This is my south pole. There are two magnets. So this is my north pole. If you want to know in detail. This is my north pole. This is my south pole. Okay, look at here. This is north pole. This is south pole. I used one DC source for creating electromagnet. This is my field winding, fixed part of the DC machine. And this is my armature, the rotating part. We call it as an armature. I use another DC source. You can have a look, X and Y. So I separately excite. For example, I can give different power here. I can give different power. It's clear to you? So the field winding, usually I give 230 volt. In lab, you can go and have a look. It will be around 230, 220 volt DC supply in standard 230. And output depends on the application. Are you going to use as a motor? Or are you going to as a generator? It's up to you to use. Now let us look at the characteristic of a separately excited machine. What I'm going to look on the x-axis, I'm going to look flux phi. The y-axis, I'm going to look at the current. What happened to this machine? If I'm going to give an excitation, you can have a look as the current increases. Which current? The Ix, the electromagnets or the field winding current. Ix increases. As it increases, the flux also increases. What is the meaning? I am making these north and south pole produce more flux. How to do that? Increase the DC power supply from 0 to maximum. So I'm increasing from 0 to the maximum of 3 ampere. You can see the flux reaches 1.25 in per unit. What is the meaning? What is the meaning of 1.2? More than 100%. I reached, for example, if my flux say 40 Weber, but I reach 40 plus 25% extra. It's clear to you? If I want 100%, what is the meaning? 100% comes exactly at 1 ampere. If I apply 1 ampere, the current here by increasing the voltage, I can get 100% flux. So this is the characteristics between flux and excitation current. So the flux and excitation current are directly proportional. It's clear? Second one, I'm going to look at for saturation curve of a DC generator. What is the saturation curve? Definition is a relationship between output voltage generated and the excitation current. What is the meaning of excitation current? The current you given to the field winding to create magnetic field. So if you are increasing the current from 0 to 3 ampere, look at here. If you are increasing the current, this current, how to increase this current? Increase the potential, increase this voltage. You are increasing from 0 to 3 ampere, the output voltage also increases. Exactly at rated or 100% of your current 1 ampere, you get 120 volt. If you are still increasing the excitation, the voltage can go up to 150 volt. So they are also directly proportional. So the generated voltage output from your DC generator is directly proportional to your excitation current. Clear? The characteristics. So if you want to increase your output voltage of your generator, what you have to do? Increase the excitation. How to increase the excitation? Increase this DC voltage between A and B. Increase the voltage. Increase the current to the coil of the field winding. Increase the flux. As you increase the flux, your output voltage also increases. Anyone can help me? So it's need a break. At 11, maybe lunch. So you want a break now or? Let me wait because it takes some time. At 11:30, we can have a lunch time, right? It's fine? Or you want now? Okay. We take a break for 10 minutes, it's fine, or you need a lunch break? Sorry, lunch break. Okay, fine. So we will meet at 11:30 is fine, or 11:20? 11:30 is fine, okay.
Yep.
Only 2 more slides finished.
Okay.
Not now, let's go for a break.
How much time are we with that? We are like half an hour.
May take little 30 because I have to talk very slowly, not very fast. 30 to 35 minutes.
Take half an hour.
Sorry, take a lunch, yes, better.
Let's talk about the problem one.
Hold on, just hold on a second. Yes, tell me.